Hello everybody, we will be studying about permutation groups. So let us start with the basic definition of what is a permutation, what a permutation is. A permutation of a set A is a 1-1 onto function from a set A to itself. So permutation is basically let A be any set and let f be any function from A to A. Then if f is 1-1 and f is onto, that is f is a bijective function from the set to itself, then we will say that f is a permutation on A. Now let us see an example. Consider a function phi from set A is equal to ABC to itself set A is equal to ABC, defined by phi of A is equal to B, phi of B is equal to C and phi of C is equal to A. Then phi is a permutation on A. So for that, let me draw the domain. The domain have three elements A, B, C, and our codomain is also same, right? A, B, C itself. And now phi of A is equal to B. So phi is mapping A to B, B to C, and C to A. This is how phi is mapping the elements of A to itself. So you can clearly see that distinct elements have distinct images. So phi is 1-1, and clearly for every element in the codomain there exists some element in the domain such that phi of that element is equal to that element of the codomain. So phi is onto also, and therefore we can see that phi is a permutation, a 1-1 onto function from set A to itself. So this is one way of representing phi. One way of representing phi was this, specifically mentioning what is the image of each and every element of the set A of the domain. Like phi of A is B, phi of B is C, phi of C is A. Now the second way to represent phi is using these diagrams. Now similarly, consider phi from A is equal to 1 to 3 to A is equal to 1 to 3. Then I can even define some another permutation phi on A as phi of x is equal to x, and let us see whether this is a permutation on A or not. So here we have defined that phi of x is equal to x for every element of A. So we have three elements in A. Phi of 1 will be equal to 1 itself, phi of 2 will be equal to 2 itself, and phi of 3 will be equal to 3 itself. Every element is mapped to itself. So this is one way to define the function. This was the second way here to define the function, and third way is using the diagram 1, 2, 3, 1, 2, 3, and they are mapped to themselves. So this is the third way to define the function phi. So this is what a permutation is, basically a 1-1 onto function from a set to itself. Now let us consider our set A as 1, 2. Alright, let us consider our set A as 1, 2, and let us see how we can define all the permutations on A. That is how we can define the all possible permutations on this set A is equal to 1, 2. What are the possible bijective functions from set A is equal to 1, 2 to itself? Alright, so let us see that. So first let me map the point the elements of the domain here, and this is the codomain 1, 2. Alright, now one way obviously by which I can make any permutation on the set A is, let me map 1 to itself and 2 to itself, right? This is what I can do, and this I can say as, say, phi of 1 is equal to 1, phi of 2 is equal to 2, right? This is how we have defined the permutation. Now let me find another way to define the permutation on A. the set A itself. Alright, so now let me again write the elements of the domain and codomain. Now earlier what I did was I mapped 1 to 1 itself and 2 to 2 itself. Now let me map 1 to 2 and 2 to 1. Alright, so now I have another mapping, say psi, and psi of 1 is equal to 2 and psi of 2 is equal to 1. These are the two mappings I have obtained. Now let me see whether there is any another possibility, any another permutation on set A or not. So I have already defined 1 to 1 itself in one mapping and one mapped 1 to 1 itself in one mapping, and in the another mapping I mapped 1 to 2. Now there is no other element in A to which I can map 1, and similarly for 2 also. So these are the only two permutations which I can define on A. So let me denote the all permutations which I can define on A by some set S. Then S will be equal to phi and psi, right? This is how I can define all the permutations on set A is equal to 1, 2. Now let us do the same exercise on the set A is equal to 1, 2, 3. That is, we have the set A is equal to 1, 2, 3, and we will see all the possible permutations on this set A is equal to 1, 2, 3. So let us start. Let me make the domain again 1, 2, 3, and codomain will be also same 1, 2, 3. Now let me map like earlier 1 to 1 itself, 2 to 2 itself, 3 to 3 itself, right? I can do this. I can map 1 to 1 itself, 2 to 2 itself, 3 to 3 itself. So this is one permutation on A. Clearly it is 1, 1 and on 2. Another permutation which I can define is 1, 2, 3, 1, 2, 3. Now what I can do is, let me map 1 to 2, 2 to 3 and 3 to 1, right? I can define the mapping like this. So this is another permutation on the set A itself, and it is different from the permutation which we drew earlier. So this is a different permutation we have obtained. Now let us try to find another permutation. So this is 1, 2, 3 our domain and codomain 1, 2, 3. Earlier I mapped 1 to 1 itself, 1 to 2. Now let me map 1 to 3 and 2 to 1 and 3 to 2. So this is how I have defined clearly the third permutation on A. Now these are the three permutations I have already drawn. Let us see whether we can draw any another permutation on the set A. So 1, 2, 3 is our domain, 1, 2, 3 is our codomain. Alright, so now another way of defining any permutation on A is, what I can do is, let me keep this one fixed to itself. Okay, let me keep this one fixed to itself, 1 is mapped to itself, and let me interchange 2 and 3. That is, let me map 2 to 3 and 3 to 2. So this is different from the previous three permutations which we drew. So this is the fourth permutation, and let us draw the fifth permutation if possible. Here, while drawing the fourth permutation, what we did was we fixed 1 to itself, we mapped 1 to itself, and we interchanged the mappings of 2 and 3. Now we can do the same with keeping 2 mapped to itself and interchanging 1 and 3. We can map 1 to 3 and 3 to 1. So this is how we obtained another permutation, which is obviously very much different from the other permutations. And now let me try to draw another permutation. 1, 2, 3, 1, 2, 3. And now I can keep 3 fixed and map 1 to 2 and 2 to 1. So this is how I can, I have drawn 6 permutations on set A, and now we have to just, be sure that there is no possible permutation, other possible permutation on this set A is equal to 1, 2, 3. So for that, this was our 1, 2, 3. Alright, let me put 1, 2, 3 here. Alright, so now there will be 1 will be mapped to definitely some element of A, right? It can be either 1, 2 or 3. So we have 3 possibilities for 1. We can map 1 either to 1 itself, 2 itself or 3 itself, right? So after mapping 1 to say some element of A is equal to 1, 2, 3, now we are left with only 2 elements. Suppose we mapped 1 to 2. So now we have only 1 and 3 left. So only 2 possibilities are left now. So now next when I am mapping 2, I have just 2 possibilities left, right? So there are only 2 choices to map 2 with. And now 1 is mapped to some element, 2 is mapped to some element, and 3 is left with no other choice, the leftover. So there is only one choice for 3. So we are having total 3 into 2, that is 6 possibilities, 6 different permutations. And this is what you can see here also. We got 6 different permutations and there is no other permutation which we can draw. Alright, so now we drew all the permutations. These permutations can even be written in array form. Alright, so how can we write any permutation in array form? We will see that. So let say alpha is any permutation on set A is equal to 1, 2, 3, so on till n. So I can represent this alpha by a 2 by n matrix, and on the top I will be putting the elements of the domain. Alright, elements of domain, and bottom I will be putting the images of the elements written here at the top. That is, under 1 we will be having the image of 1 under alpha, so let it be alpha of 1. Under 2 I will be putting the image of 2 under alpha, say alpha of 2. Under 3 I will be putting the image of 3 under alpha, say alpha of 3. And likewise under n minus 1 there will be image of n minus 1 under alpha, and here the image of n under alpha. So this is how we can write any permutation in array form. For example, now when we were making all the possible permutations on set A is equal to 1, 2, 3, we had one permutation 1, 2, 3, 1, 2, 3, we kept 2 fixed and we interchanged 1 and 3. So this is the permutation we obtained. Now let me denote this permutation by sigma. Okay, usually we denote permutations by Greek letters. So I can use square brackets or these brackets, it's alright. So on the top we will be having the elements of the domain. And here under 1 I will be writing the image of 1 under the permutation sigma. So 1 is mapped to 3, so here I will be having 3. Under 2 the image of 2 under sigma, which is 2, and under 3 the image of 3 under sigma, which is 1. Alright, so this is how I can write this permutation. Now let me consider the permutation 1, 2, 3, 1, 2, 3, where 1 was mapped to itself, 2 was mapped to itself, and 3 was mapped to itself. So let me denote this permutation by E. Then I can represent E by 1, 2, 3. 1 is mapped to itself, 2 is mapped to itself, 3 is mapped to itself. So clearly this is the array form to represent E, and this is the array form to represent sigma. So this is how we can represent any permutation in array form also. Now let us have the permutation defined on the set A is equal to 1, 2, 3, 4 as phi of 1 is equal to 2, phi of 2 is equal to 1, phi of 3 is equal to 4, and phi of 4 is equal to 3. And write this permutation in array form. This is the question. Okay, so let us see how we can write this permutation in array form. So for that, here we will be representing the permutation by phi clearly, and on the top we will be writing the elements of the domain, which is clearly 1, 2, 3, 4. Now under 1 I will be writing the image of 1 under 5, which is 2. So here I will be having 2. Now here image of 2 under 5, that will be 1. Now phi of 3 is equal to 4. So here I will be having 4, and phi of 4 is 3. So here I will be having 3. So this is the array form to represent phi, the permutation. Alright. So now in permutations we will be representing any permutation in array form, and later on we will be moving to representing permutation in the form of cycles. Okay, that we will study later. So this is how we can represent different permutations. Now, okay, so we can also represent permutations in cycle forms. So we will be seeing how we can represent any permutation in cycle form. So consider a permutation in array form, which is this. Okay, let sigma be any permutation we have, and now we will see what is meant by representing this permutation in the cycle form. So here you can observe, if we look at 1, 1 is mapped to itself. So the image of 1 is itself. Now 1 is done. Now let us see 2. So if we look at 2, 2 is mapped to 4. 4 is mapped to 3. 3 is mapped to 6. 6 is mapped to 8. And we have 8 is mapped to 2 again. So this is what we are having. So you can see that 2 is mapped to 4, 4 is mapped to 3, 3 is mapped to 6, 6 is mapped to 2, and 2 is again mapped to, 6 is mapped to 8, and 8 is again mapped to 2. So like here we have seen, we got a cycle and there is one element left. 8 is already covered, 7, and 7 is mapped to itself. So now using these cycles which I have drawn, I can represent this permutation sigma in cycle form also. So if you look at 1, 1 is mapped to itself. Now this cycle elements are 2, 4, 3, 6, 8, and I will close the cycle. Here it means 2 is mapped to 4, 4 is mapped to 3, 3 is mapped to 6, 6 is mapped to 8, and 8 is again mapped to 2. Okay, so this is a cycle, and it is in its order, it is showing how elements are mapped from one to another, and 7 is mapped to itself. Alright, so this is what we have obtained. We have obtained how we can represent any permutation in cycle form. Here if you look at this cycle, which is having just one element, it is cycle of length 1. If we look at the cycle 2, 4, 3, 6, 8, then you can see it is having 1, 2, 3, 4, 5 elements in it. It is a cycle of length 5. Alright, and 7, it is again a cycle of length 1. So we can even see what is the length of cycle. These lengths will be important. Okay. Now we can see we can represent any permutation in cycle form. And in fact, if there is any permutation which is having any cycle of length 1, we can, we can just reject it. There is no need to write it specifically. We can avoid that cycle of length 1 while writing any permutation in cycle form. So here you can see 1 and 7. They are cycles of length 1. So you can avoid them. And you can simply write 2, 4, 3, 6, 8 as sigma. And if you clearly know, if it is clearly given that this permutation is defined on the set 1, 2, 3, 4, 5, 6, 7, 8, then it is obvious, it will be self-understood that the elements which are not included in this cycle, which is 1, and 7 are mapped to themselves. Okay, the elements which are not included in this cycle are mapped to themselves. So that is why there is no need to even write the cycles of length 1 while writing any permutation in cycle form. So any permutation can be written by specifically mentioning which element is mapped to what, like sigma of 1 is equal to 1, sigma of 2 is equal to 4, and so on. Then we can even represent any permutation using diagram, right, where we will be clearly mentioning using arrows which element is mapped to which. Then we saw array form, and now in terms of cycles, and we saw the cycle form. Alright, so this is different ways to represent any permutation, and obviously representing permutation in the first two ways is very lengthy, right? Representing each permutation will take long time and large space also. So now let us move ahead and see the formal definition of a permutation sigma. What is meant by the length of a cycle is n. Okay, a permutation sigma of a set A is a cycle of length n if there exist a1, a2, a3, so on till an in A such that sigma of a1 is equal to a2, sigma of a2 is equal to a3, sigma of a3 is equal to a4, and moving on like this, sigma of an minus 1 is equal to an, and sigma of an is equal to a1, and this can be written in cyclic form as this. So let us say that sigma is a cycle. Let us say that sigma is a cycle of length n. Alright, so we know that we can even represent sigma in array form, and in array form at the top we will be having elements a1, a2, a3, so on till an. Now sigma of a1 is a2, so here we will be having a2, here it is a3, here it is a4, and so on like this. Here it is an minus 1. There can be some another elements in sigma, but they are mapped to themselves, so that is why they are not specifically mentioned about them. So this is the array form of writing sigma, and in the cycle form clearly a1 is mapped to a2, a2 is mapped to a3, a3 is mapped to a4, and like this an minus 1 is mapped to an, and an is again mapped to a1. So this is how we can write sigma, and you can see there are n elements present in sigma, so that is why we will say that it is a cycle of length n. Alright, and these other elements, they are mapped to themselves, so there is no need of writing them specifically. So this is what is meant by cycle of length n. Now if A is equal to 1, 2, 3, 4, 5, write the sigma, permutation sigma in cycle form. So let us see how we can write this permutation sigma in cycle form. So this is what sigma is. Now let us start with 1. So 1 is mapped to 3, 3 is mapped to 5, 5 is mapped to 4, 4 is again mapped to 1, so which is already there. So we can close here, and 3 is included, 4 is included, 5 is included, 2 is left, and you can clearly see 2 is mapped to itself. So this is what we have, and if we have any element which is mapped to itself, that can be avoided. Cycles of length 1 can be avoided. So we have sigma is equal to this 1, 3, 5, 4. So this is what we obtained as sigma, and it is clearly a cycle of length 4. Alright, so sigma is a cycle of length 4. Now let's write all the permutations on A is equal to 1, 2 on array form and cycle form. So earlier we already saw what are the possible permutations on set A is equal to 1, 2. Now we will write all the permutations in array form and cycle form. So we had just two permutations if you remember, and they are, one is mapped to itself, 2 is mapped to itself, 1 2 1 2, 1 is mapped to 2 and 2 is mapped to 1. These are the two permutations we obtained. Let us denote this by E and this by sigma. So E was in array form. Let us write first in array form. On the top the elements of the domain, and under the elements of the domain their corresponding images. So 1 is mapped to itself, 2 is mapped to itself. So this is what we have, E, and it is like this. Alright, so in case of identity you can say that we are just getting the cycles of length 1. So E is product of two cycles of length 1. So in this case we will be not avoiding writing E as this. We will keep it as it is. I will be telling you how we can write E in cycle form later. And before that, let us write sigma. So 1, 2 are the elements of the domain, and 1 is mapped to 2, 2 is mapped to 1. So sigma is equal to 1, 2. So sigma can be written in this cycle form as this, array form as this. Now for identity permutation, you can say here that A is equal to 1, 2. So we will be writing E as a cycle 1, 2, 1, 2. Alright, product of the cycle 1, 2 with itself. This is how we will be writing E itself. Okay, the reason of writing it like this will be told later when we will see how we can operate any two cycles. Okay, now let us see how we can write all the permutations on set A is equal to 1, 2, 3 in array form and cycle form. So we had 6 permutations I guess on total, and the first one was 1, 2, 3, 1, 2, 3. By the way, here we have 1 is mapped to itself, 2 is mapped to itself, 3 is mapped to itself. And let me denote this permutation again by E. So E can be represented as in array form. Did I represented it in array form earlier? Yes. So it will be 1, 2, 3. 1 is mapped to itself, 2 to itself, 3 itself. And E is equal to 1, 2, 3. So here also you have seen that identity is the product of two cycles. The reason why at present I am calling this permutation as identity permutation is because it is mapping the elements to itself. Any function of the form phi of x is equal to x. Okay, it is of this form. So that is why it is mapping its element to itself. So that is why. And this again you can represent by 1, 2, 1, 2. Okay, or you can even represent by 2, 3, 2, 3. You can just take any two elements from the set A and create a cycle of length 2 and write it twice. At present that is sufficient. Now after this we had 1, 2, 3, 1, 2, 3. 1 is mapped to 2, 2 to 3 and 3 to 1. So this in array form, let us represent this by alpha, is 1, 2, 3, then 2, 3, 1. And in cycle form it will be 1, 2, 3, right? And let me write the next permutation. So 1 is mapped to 3, 2 to 1 and 3 to 2. So I can represent this permutation say by beta is equal to 1, 2, 3, 3, 1, 2. And in cycle form it will be 1, 3, 1 is mapped to 3, 3 is mapped to 2 and 2 is again mapped to 1. So 2. Okay, so this is how we can represent beta. Similarly, the other three permutations that we drew, let me denote them by 2, 1, 2, 2 and 2, 3. You can try to find their mapping, their array form and cycle form also. So for the fourth permutation, the array form will be 1, 2, 3. 1 was mapped to itself and 2 and 3 were interchanged. So 2 was mapped to 3 and 3 was mapped to 2. So to1 can be represented as 1, 2, 3 like this, and there is no need to specifically mention 1. So to1 is equal to 2, 3. Similarly, to2 will be 1, 2, 3. 2 will be fixed and 1 will be mapped to 3, 3 to 1, and therefore 2 will be 1, 3. And 2, 3, for 2, 3 we will be having 1, 2, 3. 3 is mapped to itself and 1 is with 2 and 2 is with 1. And therefore in cycle form it will be 1, 2. Okay, so these are the permutations of on set A is equal to 1, 2, 3, and this is how we can write them in array form as well as cycle form. Now, the set of permutations on A forms a group under function composition called S3, the symmetric group of 3 letters. Now, if you consider the set of all permutations on this set A is equal to 1, 2, 3, they actually form a group under function composition. Okay, we will see later what is this function composition and how we can show that the permutations on set A is equal to 1, 2, 3 forms a group. Okay, so that we will be seeing later, and we will be also doing these problems where we will be seeing how we can operate any two permutations. Okay, and a few problems, and that's all for now. Thank you.